Chapter 3.1, Extrema on an interval. Day 2, more look at critical numbers. Review. If f of x is continuous, and f of 1 equals negative 5, and f of 3 equals 12, what theorem guarantees that there is a 0 between 1 and 3? And the correct answer is the intermediate value theorem. I reviewed this because this, like the extreme value theorem, is an existence theorem, in that it doesn't actually do anything. It just tells you that something is there. The intermediate value theorem didn't help us find a 0, just let us know it's there. The extreme value theorem doesn't find the extreme values, it just lets us know they're there so that we don't waste our time looking for something that may or may not exist. All right, so let's continue with this. Find the extrema. First off, make sure it's continuous. That is the condition to use the extreme value theorem. And it is continuous on the closed interval because it's a polynomial. So our first step after we have shown that the theorem applies is to find the derivative. And the derivative is 3x squared minus 12. And find where the derivative is equal to 0 or undefined. In this case, because it's a polynomial, it won't be undefined. So we can see our derivative is 3x squared minus 12. And it's equal to 0 at 2 or negative 2. However, our interval is just 0 to 4. So negative 2 does not fit our interval, so it is not important to this problem. It's good to find it, but it doesn't fit in the interval. So we'll just use the 2 and the endpoints. So when we evaluate this, we want to evaluate at 0, 2, and 4. So I'll use the table feature of my TI-84. My function is x cubed minus 12x. And I'll go look at the table, and I'll evaluate it at 0, 2, and 4. Okay, and now looking at my choices, I can see that the maximum is at 4, and it is 16. There we go. And the minimum is at 2, and it is negative 16. Okay, I can kind of use this. Help me look at the graphing window. From 0 to 4. And from negative 16 to 16. I can see I got the entire graph fitting on it from left to right. Turn the grid off so it doesn't look so choppy. Good. All right, let's look at another example. Find the extrema. G of x equals the cube root of x, all right? So this is continuous because you can take the cube root of any number, even negatives, because it's an odd root. We'll start by taking the derivative. I'm going to rewrite this as x to the 1/3. So then my derivative would be 1/3 x to the negative 2/3. We'll set that equal to 0. We got, rewrite this as 1 over 3 cube root of x squared. How do we get a fraction equal to 0? We don't. So there's no place where it's equal to 0. The other option is, where do we get it undefined? Well, how do we get a fraction to be undefined? Well, the answer is make the bottom 0. And here the bottom is 0. when x equals 0. So our critical number is 0. 0 is in our interval, so we just check our critical number and our two endpoints. So our function is the cube root of x. And we'll look at that on the table, checking 0, -1, and 1. And we can see that our maximum is 1. It occurs at x equals 1. And our minimum is -1. And it occurs at x equals -1. Okay, find the extrema here. Again, first, check, make sure the extreme value theorem applies. Is it continuous on a closed interval? We have a fraction, you can't divide by 0, but when you square a number and add 3, you're never going to get 0, so this one is continuous. And so what we need to do then, excuse me, what we need to do then is take our derivative, g prime is the bottom function, t squared minus 3 times the derivative of the top minus the top function times the derivative of the bottom, all over bottom squared. We'll clean up the top. We'll distribute our 2t. We get 2t cubed minus 6t minus 2t cubed over t squared plus 3 squared. All right, 2t cubed is in here. One's positive and negative, so we can get rid of those. We're just left with negative 6t up top. Okay, what makes the fraction 0? When the top is 0, in this case t equals 0. What makes the fraction undefined when the bottom is 0? Well, you can't square anything and add 3 to get 0, so our only critical number is 0. That is in our interval. So we will check our critical number and our endpoints to find our extrema. All right, our function is x squared divided by x squared plus 3. And we'll go to our table. We'll check 0, -1, and 1. And we can see that the maximum is 0.25, and it happens twice. That's okay. You can have a maximum happen more than once. You can only have one max, but it can happen at 2 spots. I'll show it to you graphically so you can see. And we can see the minimum is at 0, and it is 0. So if we look at this graphically, we'll set our window. We got our interval from -1 to 1. And we know our minimum value is 0, and our maximum value is 1/4. So we'll set those for our y min and y max. And we can see there that our function fits in that window with the max happening twice at each endpoint. All right, here's a slightly different way of looking at it. We want to find the extrema. Now, here the extreme value theorem does not apply because this is not continuous. So we're not guaranteed to have both a max and a min. We may have one or the other or neither. So we need to look at it and kind of use some critical thinking skills. All right, so as we look at this picture, we want to see if we can find a relative max and a relative min. Okay, a relative max is a point defined as being higher than everything else in the function. All right, that would be right around here. However, this is an open interval. That is an open circle. So that is a boundary. We don't actually get to that point. So here we would say the relative max does not exist, right? Because say if this point is 5, we got an open boundary at 5. That means we can get right up to 5 but not quite touch it. So why doesn't 4.9 work? Well, what about 4.99? Or what about 4.999? There's always a number you'll be able to fit between your interval, your number, your endpoint, and the one you've got before, right? There's always a space for another 999. Relative min is right here because this is a closed circle. So the relative min is right there. Whatever it is, it reaches that point. Say it's 2. Our relative min is 2. Say it's 3. Our relative min is 3. And here's another picture. Again, it's discontinuous at that jump, and it's a open interval, so we're not guaranteed to have a max or a min, but we can still look for it. And actually, we're looking for an absolute max. I should go back and change the last problem. Absolute max does not exist, and the absolute minimum is right here. All right, in this one, whoa, excuse me. In this one, we're looking for the absolute max and the absolute min. If we take a look, the absolute max, or the max would be around there, but again, that's an open circle. So here the maximum does not exist. And the min would be right around here, but again, this one is an open circle. So because it's an open circle, it's a boundary that has an endpoint that we don't quite get to. There is no relative min. Or absolute min, sorry. If we take a look at this picture, open interval, discontinuous, no guarantees. And as we look at it, the max would be either here or here, depending on which is higher. I believe the left side is higher. However, it's an open circle, so it's a mute point. The max does not exist. And the min would be down here at the cusp, except for the fact that that's an open circle. The min does not exist. All right, a few more. Again, take a look. Our relative max, you can see at the top there's 2 open circles. So our max does not exist here. But our min, in this case, is right there. Whatever that value may be, because it's a closed circle, that minimum does exist. Take a look here. Is there a relative max, or an absolute max, or an absolute min? Well, look at the open and closed circles. We can see that there is no max, and there is no min, because there's open circles, both at the max and the min values. And finally, let's go orange here. Max? Nope, open circles, no max. Is there a min? Yes, the min in this case, because there's a closed circle, this one has a minimum value right there, whatever it is, say 1 between A and B.